So today I'm going to talk about modeling our continued effort on modeling sequences of earthquakes and aseismic slip with high resolution fault zone physics. This work was primarily done by now Dr. Mohammed Abdelmegid, who defended his thesis a couple of weeks ago. And hopefully Dr. Tabim Ahmed Maya, we'll see if we can help him get a PhD himself too. So our starting point is, as Alice mentioned, fault zones are complex, and probably most of us are familiar with this classical figure from Mitchell and Faulkner, that whether you consider a fault zone consisting of a single core or multiple core, it's evident that there is some persistent localized zones within dynamically evolving fault zone that combines discrete and distributed damage feature, and that structure is continuously evolving, but luckily with some long-lived statistical properties. And in such a setting, volumetric and deviatoric deformations are naturally coupled, but as expected, the processes may be depth dependent in terms of what mechanisms are dominant, as well as how this structure would look near the surface versus at depth. And unfortunately, observations are limited. We are getting more and more observations, but not close enough from the fault to constrain this complexity, and hence simulations are needed. And ideally, what we would like to do is to build a virtual earthquake machine where we can track the evolution or the co-evolution of stresses, fault zones, and constitutive description in the bulk in a self-consistent way. Of course, one can think of an approach of running single dynamic rupture simulations with different initial conditions and look at the ensemble of the results, and that's a valid approach. However, the limitation is that we don't think the earthquake system is ergodic. So ergodicity is not guaranteed. So randomizing initial conditions may not put you in the right attractor where the self-consistent statistical properties are observed. And hence a simulation framework that we can track for a specific system, how it evolves over a long period of time is needed. And that's what the SEAS framework, sequence of earthquakes and aseismic slip simulations framework, is attempting to achieve. But of course, there's no free lunch here. And the challenge is that there's a wide range of spatial and temporal scales involved in this problem. And I really like the video by Selvan and others, which is an introductory video to this workshop, where he gave an overview of the different numerical techniques that many of us are trying to do in order to slay that dragon of the conundrum of scales. Here, I will focus on maybe a specific class of problems that we think are important, where complexity is spatially localized and in a relative sense. And in a relative sense here, I mean that the spatial distribution of the complexity is not wide enough that it covers the whole domain that we are interested in. And also it's nor limited near to the fault surface such that it can be lumped as an effective constitutive description. So it's somewhere in between. And we encountered this, for example, in damage zone, where damage zone width can extend for several meters over fault length that span kilometers. We also observed this in dynamic rupture simulations with plasticity or damage, where the damage is localized near the fault, but has important details and influence on the near field solution that it cannot just be lumped or homogenized as an effective friction law. And our tool to address this class of problems is what we come up with. It's called Phoebe, and Phoebe is a hybrid numerical scheme that combines finite element and boundary integral or boundary element techniques. And the way Phoebe operates is that spatially, it approaches the problem through domain decomposition. So imagine you have some sort of structural complexity limited to the fault surface, limited to the near fault region. So what we are going to do is to encompass this structural complexity in what we call a virtual strip, and we can discretize this virtual strip using finite element, finite difference, discontinuous Galerkin, any of your favorite volumetric or domain-based approaches. But then we cannot forget about the exterior half spaces, because this is where this is our loading machine where waves will propagate and strain energy is stored. So what we do is we replace the exterior half spaces by an effective boundary integral description. So on the boundaries of this virtual strip, we have a boundary integral formulation that relates the traction to the displacements and velocities on that virtual strip. And the way we couple these two is by enforcing continuity of traction and displacement across the interface. Temporally, we use an adaptive time stepping technique, which cycle between quasi-dynamic approximation to simulate aseismic deformation and fully dynamic with full inertia effect to simulate seismic rupture. And we switch between these two techniques based on a velocity threshold. And for those of you who are interested to learn more about the details of the method for single dynamic rupture as well as quasi-dynamic cycle, the references on the right here shows this, and then the references on the left shows applications of Phoebe to fully dynamic cycle simulation, which I will be talking about today. So let's consider one approach or one application of engaging the bulk through a nonlinear rheology and looking at how this nonlinear rheology would affect the evolution of seismicity and stresses. So for that purpose, we consider an idealized problem of a planar rate and state fault in a 2D plane strain approximation. And the bulk here is described by an elastic viscoplastic Drucker-Prager formulation. And these are the equation of the Drucker-Prager formulation. Two features here that we consider. It has a viscous component that gets activated once the stresses exceed the yield strength. So there's some time dependency, but it's not as in the regular viscoelastic case. It's only triggered once the yield stress is achieved. And then the other important feature is that the yield surface is or the strength of the bulk is parameterized by two parameters, a cohesion and an angle of internal friction. And importantly, the strength is pressure sensitive. And as I will show in the next slide, this actually is really important when looking at the evolution of seismicity and stresses. I look forward to the discussion where we can discuss the merits and limitations of plasticity versus other damage mechanisms. But for the purpose of this talk, I would like to highlight that, okay, plasticity has some advantages. It's a dissipative mechanism. It enables incorporations of inelastic volume changes. And it's a simple tool to study the partitioning of deformation between fault slip and the inelastic bulk. But definitely it has some important limitations. It doesn't account for healing. It doesn't also enable tracking the evolution of elastic properties and the impact on wave speeds and subsequent healing. So these are things that we are actively working on right now, but I leave them for future work. And just before leaving this point, these are, here I list a few references that addresses this point, this kind of problems with different approaches and limitations. And I would just like to emphasize that this whole effort to engage the inelastic bulk in cycle simulation is still in its infancy. So there's a lot of work to be done. Most of the results I'm going to show today is in this paper by Mohammed and myself, and this is going to appear soon in JGR, but it's also available in ASOSAR. So back to this point about the pressure sensitivity, and I here illustrated with this figure, which shows a right propagating rupture tip on a fault with a right lateral sense of slip. And as you see here, the rupture tip would carry perturbation in the mean stress such that the upper quadrant would experience more compression and the lower quadrant would experience tensile perturbation and hence less compression. And when the yield surface or the strength is pressure dependent, then this means the upper quadrant, which has more compression, would be stronger, and the lower quadrant would be weaker in some sense and more prone to the accumulation of plastic strain. And this is a figure from Templeton and Rice, which definitely speaks to this kind of directional accumulation of strain accumulation. This, of course, is dependent on the angle of maximum compression. So it depends on the background tectonic stresses. For this particular talk, I will just focus on one angle of maximum compression, and this is 45 degrees. And for that angle, the dynamic rupture simulations, which are shown here in Templeton and Rice, shows definitely that the plasticity is accumulating on the dilatational quadrant. So let's see what happens if this persists as we look into the cycle simulation. And what we observe is that for relatively strong bulk, and we can parameterize the bulk by cohesion, for example, if we add more cohesion to the bulk so that the yield strength is higher, we do see this conservation of the observation related to the accumulation of plasticity on the dilatational quadrant. So in the upper figure here, we saw that plasticity after many events, the accumulated effect, cumulative effect, is showing that plasticity is accumulating predominantly on the dilatational quadrant. But interestingly, if we start reducing the strength of the bulk, we start seeing a more drastic changes. Plasticity is observed to accumulate on both sides of the fault. And eventually we see not necessarily a symmetric distribution, but plasticity is filling the domain near the fault. And there's really no much distinction for the dilatational versus the compressional quadrant. And we were puzzled by this, but we needed to look further into the mechanism that enabled this kind of distribution of plasticity on both sides of the fault. And we came up with three kind of mechanisms for this. The first one is clearly rupture can propagate from left to right or right to left. And depending on the rupture directivity, the stress perturbations carried by the rupture tip would be different as you look at the rupture tip from different quadrants. So that's one reason. Another reason, which is really specific to the cycle simulation, is that during the interseismic period, we have aseismic slip fronts advancing into the velocity weakening region. And these creeping front carry their own stress perturbations, so they can influence the tension and compression perturbations differently from the seismic rupture propagation. And also, they may also carry their own plastic deformation. So there's an effect here that coming in the interseismic period that will affect the subsequent coseismic plastic strain accumulation. And the third effect here, which was pointed out actually in Templeton and Rice, is that there's also a co-evolution of the mean stress and plastic strain accumulation. For example, here, I'm showing an example of a single dynamic rupture, and the mean stress changes in that dynamic rupture. And you could see that in this black dotted rectangle, there's actually more compression accumulating, or compressive stress perturbation accumulating in what's supposed to be the dilatational quadrant. So this compressive perturbation is mainly localized on the side where plasticity has accumulated. So when plasticity accumulates on the tensile part or the tensile quadrant, you get more compressive perturbation and vice versa. So you could imagine in a cycle simulation that you get this continuous feedback between plasticity and mean stress. Plasticity changes the mean stress, and then the mean stress would also change the yield surface. And so you get into this positive feedback. So after understanding this interesting evolution of plastic strain accumulation, we looked into the impact on seismicity. And here I'm showing just a few examples. When you get an elastic reference case, you didn't engage plasticity at all. For the parameters we considered and fault geometry length we are interested in, we get just periodic events that are fault spanning as well. But as you start engaging plasticity, we observe a transition from a kind of quasi-periodic, or at least clusters of events, to completely spatiotemporal complex distribution of events. And this happens as the bulk becomes weaker. So there's a transition between more localized slip on the fault surface approaching the elastic case where no inelastic deformation is happening to the bulk, to this extreme other end of the spectrum where more deformation, and we'll see that this is not significantly more, but some inelastic deformation is accumulated in the bulk here. And as I mentioned, this complexity is correlating with this partitioning of deformation. This plot here shows integrated plastic deformation versus the potency for different values of cohesion. And as you can see, as we reduce the cohesion, we get more integrated plastic deformation in the bulk. Is still, I just point out to the scale here, this 10 to the power -3, this 10 to the power -1. So still the total plastic deformation in the bulk may be 1% of the potency. However, its impact is quite significant. So let me show you a couple of videos that walk us through some details of how the evolution of the mean stress and seismicity interplay in this situation. I will start with this video that shows how coseismic plasticity accumulation is influenced by the residual stresses from the prior history to the extent that it actually accumulates more in the unexpected quadrant. So let me play this video here. This rectangle is the expected location based on the dynamic rupture simulation. And as you can see, the top here is the slip rate, the middle is the plastic strain, and the lower figure here shows the mean stress. So let me play it one more time. So as the creeping front advances, you get perturbation in the mean stress, but you can see that more plasticity here is accumulated on the opposite side of what we expected based on the direction of propagation. That's basically because of the tensile perturbation that was carried by the advancing creeping front. So one more time. Okay, so let me move on to the next video. And the next video would show a coevolution of the plastic strain and near fault mean stress here. This is over the whole cycle. You would see the plastic strain accumulating in the middle section here, and the bottom section, you see the evolution of the mean stress as multiple events starts propagating. So we are approaching this goal of trying to simulate the seismogenesis of fault zone because we are seeing how this damage region is evolving over cycles. And as it evolves, it actually changes the stress and feeds into the future seismic events. And then finally, I would like to show you this video that it's quite long, but I'll try to accelerate it because I want to emphasize here how plasticity could also lead to intermittent nucleation and event propagation. So let me just start here and look at the plastic strain accumulation as the slip rate below is advancing. And I will accelerate. You will see that little patches of plastic strain can accumulate ahead of the rupture tip because of the interaction between stress perturbation and the residual stress field, and focus on the left propagating tip, which would take place in a little bit. So as the left propagating tip advances, you start seeing segmentation of the plastic strain. So propagation of the rupture tip, arrest, and then accumulation of plastic strain ahead, and then eventually the system takes off and the dynamic event propagates coherently. Through this kind of intermittent nucleation, delayed nucleation, rupture arrest, and rupture jump is evolving naturally in this kind of sequence simulation. And one thing that was surprising to us is as we look at the end results of the simulation, we also see, for example, evolution of the fault surface profile. So remember, we started with a planar fault, but if we look at the profile of the fault at the end of the simulation in the transverse direction, we actually see that it develops quite significant undulations on both long wavelength and short wavelength. This scale here is in millimeter. And when you translate the nucleation length here, this horizontal scale would be tens of meters. So we are actually, maybe this is an order of magnitude less than commonly observed fault roughness, but this is something that evolves naturally as part of the simulation here with very simple input and constraints. And more importantly, this evolution and of the fault surface also correlates with a strong variation in the normal stress that starts to emerge on the fault due to the partial rupture and the plastic deformation. So that's another interesting observation we have in this simulation. So if we move on to some of the output that comes from these kinds of simulations, we can look, for example, at how damage changes as a function of the distance normal to the fault. And we see, if we look at either below or above the fault, we definitely see that the damage density as measured by the plastic strain accumulation is decreasing as a function of distance normal to the fault. And although our simulations are under high confining pressure, this kind of agrees with observations at the surface for the fracture density as a function of distance from the fault. So perhaps some of what we are seeing at the surface is also translated to the depth. Of course, we cannot be sure until we do 3D simulations, but this is just one a conditional observation. The other thing is that the damage width also increases with accumulation of slip on the fault, but potentially saturates after a slip threshold. And this is also kind of similar observation to what Savage and Brodsky have observed near the surface. So let me take just, and then this is the last slide for this section that shows, as I showed in the video, there's actually complexity in the stress field, and we get alternating quadrants of dilatational and compressional changes. And this was recently observed in experiments, and some connections were made to also radar observations for the San Andreas fault, this alternating compression and tension deformation. So let me just take the next few minutes to show you other modeling attempts that we are looking at in terms of the structure complexity. Here's an example of a step over simulations that Mohammed and Showman are carrying out. And once we start looking with these kinds of structure complexity plus plasticity plus inertia, we start seeing very interesting observations, not only in terms of the seismicity, but also in the terms of how the faults are speaking to one another and how the stresses are evolving in that region. So for example, here you see this is one complex sequence of events in the middle of the cycle, where we see that a rupture on one fault have changes the stress condition on the other faults. So you get another rupture here, and then a partial rupture, triggered slow slip on one of the faults, and then you get some sort of rupture jumping and so on. We also see a co-evolution of the stresses and the plastic strain. You see again an example of seismogenesis here. You get a heavily plastically deformed region with some branches here that looks like the horsetail kind of structural features that people observe in these regions. And associated with this, we see a big increase in the compressive stresses, in the mean stress. The mean stress that we started with here was 50 megapascal. After many cycles, it can actually reach here 300 megapascal. And if we keep simulating, it increases more. So we are also learning about limitations of constitutive model. How does rock behave under increased confining pressure in that way? If we start with Drucker-Prager plasticity, is it actually valid as we push it further, or do we need to engage other constitutive models like damage or fragmentations and so on? And finally, we also see a very steep change in the stress rotation as we approach this step over region. So outside the fault step over region, we get the background tectonic stress. But as you approach, for example, the horsetail region here, you get tensile stresses. And within this overlap region, you actually get a strong rotation in the stress field. So over small distances, you can get rapid changes in the stress rotations, which can be also tested through borehole breakouts, etc. And finally, I want just to give, and I know others would talk about the spectrum of slip. Here's a spectrum. Here's an example of what we observe as we reduce the strength of the bulk. It's still stronger than the fault, but as we go further into weaker bulk, we do observe a very rich transition in the slip behavior here. We can actually go all the way to completely locked, stuck fault, even if it's velocity weakening, if there is enough plasticity accumulating in the bulk. For example, this is the case I'm showing here, to cases where you observe the emergence of small repeating earthquakes naturally without prescribing rheological heterogeneity on the fault surface. And then you can also look at evolving earthquake gates where you get some temporary locked region that eventually get ruptured through a dynamic rupture and then gets locked again and so on. So one more minute just to cover this ongoing work. So there's a lot to be done within this framework. We listened yesterday to beautiful talks about fluids. So definitely boromechanics is something we are interested in. We made progress in incorporating poroelasticity in finite element, but then there's still, we need adaptation for our spectral boundary scheme for poroelasticity, and then eventually also incorporating poroelastoplasticity in the finite element strip. Continuum damage plasticity and evolving elastic properties and wave speeds are really important. And I know Yihi would talk about some of this effect in the next, perhaps, talk. So this is another thing, another important feedback mechanism that we are interested in. And then finally, the true fault seismogenesis, where we can actually go through the nucleation and growth of faults. And we are using a variety of techniques here, like phase field method, as well as causal space-time discontinuous Galerkin approach to approach this problem, which would be important as we think about this idea of next generation earthquake simulators that Alice, Yehuda, and I are trying to formulate. So in conclusion, I hope I showed in this presentation that Phoebe provides a tool for investigation of complex fault zones, keeping the computational costs manageable. So indeed, there are other techniques that can achieve similar conclusions here, but that was our choice. And then partitioning of deformations between fault slip and off-fault plasticity contribute to the emergence of seismic complexity. And then in the slides I showed, the width of the plastic zone and the amount of deformation accumulating in the plastic zone is really small compared to the fault length or fault slip. However, the impact on source physics can be substantial. And so it's really important, I think, to keep exploring this highly nonlinear near fault region, because by doing this, we can understand the source physics better. And as a Star Trek fan, I think we can even at some point control earthquakes. So thank you very much.